Electric field is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now, the electrostatic force we were introduced to in the last lesson is a field force just like gravity, and it can operate at a distance. It is not dependent upon two objects being in contact whatsoever. Now, in addition to dealing with some of the math and some calculations involving electric fields, we're also going to learn how to properly draw electric field lines in this lesson as well. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So let's dive right in by taking a look at the mathematical relationship between force and electric field. So it's a rather simple relationship, F equals QE. So and the force here is also electrostatic force. So we saw that Coulomb's law gives us one expression for the electrostatic force. Here's another one that just relates it very simply to the electric field at a given point in space. What do you need in order to feel gravity? You need mass. Well, what do you need to feel electrostatic force? You need charge, and that becomes part of the equation here as well. So the electrostatic force is proportional to the magnitude of the charge that's experiencing the force, but also proportional to the magnitude of the electric field at that point in space. And if we rearrange this and solve for an expression for the electric field, we get force over charge. And that's going to let us see that the SI unit for electric field is Newton per Coulomb. All right, so you might do some simple plugging and chugging with this. If you know the magnitude of electric field at a point in space and you want to know what is the electric or electrostatic force experienced by some charge of some magnitude, you simply just multiply the two together to get the magnitude of the electrostatic force. And that can be rather easy. Now, even if you don't know why there's an electric field at that particular location, as long as you know its magnitude, you're good. Now, what causes an electric field? Well, charges do. And it might be just one charge. It might be a multitude of charges. If it's just one charge, life is easy, and we're going to derive a simple expression for what the electric field caused by a point charge is. But if it's a multitude of charges, you might have multiple contributions to this electric field, and you would add them together as vectors. So the electric field is a vector. You would add them together as vectors, so you might have to break them up into x, y components, all that. But once you knew the overall magnitude and direction of the electric field, you could then very quickly calculate the electrostatic force experienced by a charge of given magnitude at that location. Now let's go take a look back at Coulomb's law for just a second. We'll have a positive charge and a negative charge. And Coulomb's law said that F equals K times the absolute value of Q1 times the absolute value of Q2 all over the distance of separation squared. And I'm going to write that just a little bit different, but that Coulombic force, that's the electrostatic force experienced by either of the charges. And the force that either one of these feels is equal in magnitude but opposite in direction. And we know that unlike or opposite charges attract, so for the positive charge, it's feeling an attractive force to the right. For the negative charge, an attractive force to the left. But the magnitude is exactly the same, and in either case, the magnitude is given by Coulomb's law. I'm going to write that just a little bit different for these. I'm going to label, so the positive charge is Q1 and the negative charge is Q2. And so I'm going to write this just a little bit different. So Coulomb's law could also be written as Q1 times K times Q2 over R squared. And over here, I'm going to write it as Q2 times K times Q1 over R squared. And we want to match this up with our new expression relating electrostatic force and electric field. So F equals QE, F equals QE. When we write it this way, the Q is the Q of the charge that's experiencing the electrostatic force. So in this case, that would be Q1, and over here, the force is being felt by Q2. But again, point charges not only can feel electrostatic forces, they also can cause electrostatic fields that can result in another point charge feeling an electrostatic force. And so here, why does Q1 feel an electrostatic force? Well, it's because Q2 is causing an electrostatic field to exist at Q1's location. Why does Q2 feel an electrostatic force? Well, it's because Q1 is causing an electric field to exist at Q2's location. This gets a little bit confusing. That's exactly how it works. And in either case, though, you can see that we can come up with another simple expression for the electric field caused by a point charge. And it's equal to K times Q over R squared. And so it turns out we get this electric field everywhere around a point charge. But the further you get away, the smaller the magnitude of the electric field is going to become. Another inverse square law as we see. So if you double the distance away, the electric field is going to go down by a factor of 4 in that case. All right, so students sometimes get confused about, who's Q1 here and who's Q2 and how do I, turn this into QE and things of the sort. Well, again, the Q in F equals QE, that Q is the magnitude of the charge that's feeling the force. So, and why is it feeling a force? Because there's an electric field caused by the other point charge at its location. Okay, now we're going to talk about the direction of the electric field as well. And it turns out with positive and negative charges, things get a little bit confusing. Now, we dealt with gravity, so there was only one kind of mass. It wasn't like there was positive mass and negative mass, or mass and antimass. So, and there was only an attractive force. But now, because there's now an attractive force and a repulsive force, and there's two different types of charge, things get a little confusing. And we'll find out that in almost every case, things were defined in the context of talking about a positive charge. And then just know that for the negative charge, things tend to be the opposite. Same thing for electric field here. So if we take a positive charge, and we're going to call this an imaginary positive charge, and put it in between Q1 and Q2 here. So, and we're going to talk about, well, what is the direction of the electrostatic force that would be experienced by this imaginary positive charge. This imaginary positive charge is more commonly called a positive test charge. And in this case, it would feel a repulsive force from Q1 here, which would point to the right, and it would feel an attractive force to Q2, which would also point to the right. And two forces pointing to the right adds up to a bigger force that points to the right. And so the force it would feel points to the right. Well, it turns out that the electric field always points in the direction, the same direction as the force felt by a positive test charge. So not only does the force felt by this test charge, this positive test charge, point to the right, but the electric field points to the right. Now, what's tricky about this is whether we have a charge at that location or not, there's an electric field that's going to be defined and it's going to point to the right. Because what if instead we actually didn't have a test charge but had an actual negative charge at that location? Well, again, the direction of the electric field is defined as if there were a positive charge there, and it would still point to the right. It points in the same direction as the force experienced by a positive test charge, whether or not there's a positive charge there or not. In this case, the force experienced by that negative charge is going to point to the left. It's attractive to Q1, repulsive away from Q2, and the force is going to point to the left. But the electric field, by definition, is still going to point to the right. So be careful with that. So again, the direction of the electric field is always in the same direction as the force felt by an imaginary positive test charge, whether you actually have an imaginary positive test charge or not. All right, this makes a good transition to talking about what we call electric field lines. And electric field lines are a great way to kind of graphically give some indications about the electric field in certain areas. So a couple rules about electric field lines. So electric field lines usually originate from positive charges and terminate on negative charges. So now it turns out that sometimes, if there's no balance of charge in your diagram, you might have multiple positive and negative charges. Well, if there's excess positive or negative charge, you may have some of the field lines originating infinitely far away, not actually originating on the diagram. They're coming from outside the diagram. Or you might have them terminating infinitely far away and kind of just exiting the diagram. But if the charges are balanced, then every field line should either start from a positive charge or end at a negative charge, never the other way around. Now, there's also a quantitative nature to these electric field lines as well. So these electric field lines we draw as arrows. So the number of arrows corresponds in some way, shape, or form to the magnitude. Now, it's not like, there's a number value assigned to every arrow. What there is, though, is a relationship. So if these two lovely point charges were on the same diagram, then I could come to the conclusion that they have the same magnitude of charge. Now, I might not know what the charge is if it's not given, but I can conclude the same magnitude because the number of field lines originating from this positive charge is exactly the same number of field lines that's terminating on this negative charge, and that's how I would conclude they have the same exact magnitude. Now, if the number of field lines was not the same, whichever one had less would be a charge of lower magnitude, whichever one had more would be a charge of greater magnitude. Also, because if you have greater positive charge or greater negative charge, you're going to have more field lines around it. So, and then you're also going to have more field lines that are going to be closer together as a result too. And so it turns out in general, the closer field lines are together, that kind of symbolizes a stronger electric field at that point in space as well. So just a couple things to keep in mind for properly drawing electric field lines. On the study guide, and I'll put it up on the screen here, there's also a picture of an electric dipole that kind of shows if these two might be part of the same diagram. So fixed in space, but positive on one side, negative on the other side. And you'd find that electric field lines would start at the positive charge, terminate on the negative, and they wouldn't just go in a straight line though. You'd have them curving in space from one to the other and stuff as well. And the further you get away, the further the field lines would get away as they make their way around, symbolizing that the further you get away from these charges, the lower the value of the electric field there as well. All right, so from here, we're ready to do a little bit of plugging and chugging. First question we're going to do here says, what is the electrostatic force acting on a 1.0 microcoulomb point charge in a region where there is a constant electric field of magnitude 8.0 newtons per coulomb? We'll start there. Well, again, we've got the magnitude of the charge, we've got the magnitude of the electric field, and it's simply Q times E to get that electrostatic force. And so in this case, Q times E is just going to work out to give us 1 times 10 to the negative 6 coulombs times 8.0 newtons per coulomb. And we can see that this is going to work out to give us 8.0 times 10 to the negative 6 newtons. The coulombs will cancel. Okay, so there's the force. Second half of the equation, though, says if the mass of the point charge is 0.0020 grams, what is its resulting acceleration? And so in this case, we know the net force acting on it. We know its mass. Now we want to find its acceleration, and that's just Newton's second law here in this case. And we'll use F equals ma. And if we rearrange the solve for acceleration, it's equal to force over mass, which in this case was that force of 8 times 10 to the negative 6 newtons. And here the mass is given as 0.0020 grams. That's 2 times 10 to the negative 3 grams. But again, this has got to be in kilograms, SI units, and that's going to be 2 times 10 to the negative 6 kilograms. And in this case, we can see that this is going to come out to exactly, we want 2 sig figs, but 4.0 meters per second squared for that acceleration. So again, a force of 8.0 times 10 to the minus 6 newtons, an acceleration of 4.0 meters per second squared. So the last question here comes with this lovely diagram, and question says, for the following arrangement of point charges, at what location along the horizontal axis is the electric field 0? So at some point here, so we know electric field due to point charges is kq over r squared, and at some point along this axis, or at least in one point anyways, somewhere we're saying that it has to be 0, and there's two things contributing at two different point charges, but at some location it's going to be 0. And we've got really 3 different regions to consider: left of both point charges, in between the 2 point charges, or somewhere to the right of both point charges. And we first want to take a qualitative look at those 3 different regions, so maybe we can rule some of them out. And the first one I want to take a look at is in between. Not because there's any rhyme or reason, just because I know it's going to be one of the ones we rule out pretty quickly. Now, if we take and envision having a positive test charge right in the middle there, so the idea is this. We said that the direction of an electric field is the same as what the force felt by a positive test charge. If we can come up with a region where a positive test charge might not feel any force, that would be the place where it might not have an electric field as well. All right, so in this case, it's going to feel an attractive force to the negative charge on the left. That's going to be a force pointing to the left. It's going to feel a repulsive force from the positive charge on its right, so that's going to also point to the left. And so these 2 components to the force that this positive test charge would feel both point to the left. And again, depending on where in this region you put it, no matter what though, the magnitude of how much these point to the left is going to change, but they both point left. When you add them together, you're going to get a bigger resultant force pointing left, no matter what. Well, there's no way, therefore, there's a no net force, and therefore no 0 electric field possible there as well. Now, if we consider a location over here on the right, so here, with the negative charge here, there's going to be an attractive force pointing to the right, but a repulsive force from the positive charge over here that would point to the left. And if there's a way that these 2 components might be equal in magnitude, since they're opposite direction, they could potentially add to 0. We can't just rule it out right off the bat. Same fashion on the other side. There's a positive test charge here. There's going to be a repulsive force felt due to the positive charge and an attractive force felt to the left due to the negative charge. And again, they're in opposite directions. If it's possible for them to be equal in magnitude, these 2 components, but opposite direction, then it could be 0. Now we'll keep in mind a couple other things here. So your electric field is proportional to the magnitude of the charge, and it's inversely proportional to the distance of separation squared. Now we also want to then consider which of these might be larger based on those considerations. So we'll go back and start this process over again. I know the directions, but I also want to represent the magnitudes now by bigger and smaller arrows. And so here, from a charge standpoint, which one of these two charges is going to cause a larger electric field? Well, whichever one has a larger charge, because electric field's proportional to charge. So based on charge considerations alone, it's the direction of whatever the positive 9 microcoulomb charge causes. For this positive charge over here, that's going to be the force pointing to the left. That's going to be the larger one, based on charge considerations. But for distance, the smaller the distance, the larger the impact, the larger the magnitude of the electric field. And it's closer to the negative charge, which is contributing a component pointing to the right. And so all of a sudden, there's going to be possible for these to be equal in magnitude. So one's larger based on charge considerations, one's going to be a larger component based on distance considerations. At some point, at some distance to the left of both of these charges, those potentially could have the same magnitude and add up to 0. On the other side, we're going to see that's not going to be possible. Based on charge considerations, again, the 9 microcoulomb charge is bigger. That's a repulsive. The larger force, and larger electric field is going to point to the right. It's also the one that's closer to this charge over here, anywhere over here. And so based on distance considerations, the bigger one is also still going to be the one pointing to the right. The one to the left is going to be smaller in any case, no matter where you stick it over here. And there's no way for these two components that point in opposite directions to be equal in magnitude. No matter how you add them, you're going to get a net force pointing to the right, regardless of where you envision the location to the right of both these charges. So this is going to be the one that we have to consider. The other two we've kind of ruled out, and now we've got a little bit of math to do. So, and we're going to do this the easy way and the hard way. It turns out I picked some really nice numbers here so you could kind of reason this out, but much of the time you could kind of ballpark this out a little bit. Now, we said that the electric field's proportional to Q. So, and again, somewhere over here, based on charge considerations alone, we know that the 9 microcoulomb charge is going to have a larger impact on the electric field. Its component's going to be larger. How many times larger? 9 times larger, because 9 microcoulombs is 9 times bigger than 1 microcoulomb. So based on the fact that electric field is proportional to Q, 9 times bigger based on the 9 microcoulomb charge. Okay, now which one's going to be larger based on the distance of separation? Well, it's going to be this one. And I need R squared here to be 9 times smaller for the negative charge. So again, there's an inverse relationship. So if I want the electric field to be larger for the 1 microcoulomb charge here, so which is pointing in the opposite direction, so I want it to be closer. Well, it is closer. I need it to be a certain amount closer. I need R squared to be 9 times closer. And if R squared is 9 times closer, that means R, take the square root, is 3 times closer. And so we can take a look at this distance right here, which I'll call x, and compare it to this distance right here, which is 10 millimeters plus x. And ultimately, I need x to be 3 times closer than 10 plus x. And you could write that as an equation. You could say that x equals 1/3 of 10 plus x, and then solve for x. And so in this case, I'll multiply both sides by 3, and I'll get 3x equals 10 plus x. I'll subtract x off, and we'll get 2x equals 5, and therefore x, 2x equals 10 still. Let's get that right. Divide by 2, and you get x equal to 5. And all of a sudden, we see that x is going to need to be 5 millimeters left of the negative charge. And that way, this distance right here would be 15 millimeters, and that's exactly 3 times bigger. 5 millimeters compared to 15 millimeters, exactly the relationship we said we needed. Now, if the numbers weren't nice, you could still kind of ballpark this in your head, and that way when you calculate the answer, it might make sense. But how would you actually go about solving this? Well, what you'd ultimately do is you'd say kq1 over r1 squared plus kq2 over r2 squared. It's going to add up to 0. This is what you'd ultimately do. I'm going to leave the k's in there for a minute because they're going to cancel anyways. In fact, I could cancel them out right now. I could divide the whole equation, both sides by k, and it would fall out, but I'll leave them in there for now. K times Q1. I'll make Q1 this 1 microcoulomb charge, so 1.0 times 10 to the negative 6 coulombs. And the distance of separation here we called x. So, and in this case, the force felt by a positive charge is going to be to the right, so the electric field is going to be to the right, and I'm going to call that the positive x direction, so make this term positive. And then for Q2 here, I'm going to make that the 9 microcoulomb charge, and we're going to have K times 9 times 10 to the negative 6 coulombs all over R2 squared, which is going to be 10 plus X quantity squared. And in this case, relative to the positive charge over here, it's going to be a repulsive force pointing to the left, which means there's an electric field pointing to the left. So I'm going to make that negative, and these are going to add up to 0. All right, the algebra here is a little worse than the equation we solved here, but ultimately reduces down to the same thing, as we'll see. And so in this case, we rearrange this just a little bit. So K times 1.0 times 10 to the negative 6. I'm going to leave off the units to make this a little bit easier. All over X squared. So I'm going to add this to the other side. So K times 9 times 10 to the negative 6 all over 10 plus X quantity squared. And a couple things we can see. One, I can definitely divide out those K's, but also I can divide out these 10 to the negative 6's to make my life a little bit easier as well. In this case, this reduces down to 1 over X squared equals 9 over 10 plus X quantity squared. You got a couple different paths you can choose here. So you can do some cross multiplying, and you could FOIL this 10 plus X quantity squared out and stuff like that. Or you might realize that you've got perfect squares on both sides. The square root of 1 is 1. Square root of X squared is X. Square root of 9 is 3. Square root of 10 plus X quantity squared is just 10 plus X. Because you got perfect squares in both the numerator and denominator on both sides, you can just take a square root and make your life a lot easier. And so in this case, we're going to get 1 over X equals 3 over 10 plus X. And now I'll cross multiply. We'll get 3X equals 10 plus X. I'll subtract off X, and I'm going to get 2X equals 10. And once again, X equals 5, just like we saw here. But ultimately, the final answer could be phrased in a couple of different ways. We could say that the location where the electric field is 0 is at a point in space located 5 millimeters left of the negative 1 microcoulomb charge, or it's at a location in space 15 millimeters to the left of the positive 9 microcoulomb charge. Either one of those obviously correct. If you found this lesson helpful, consider giving it a like. Happy studying.